Hi everyone. In the previous video on introducing the MLE, I ended the video by showing you an example when the usual method of solving MLE does not work. Just to recap, I have a model consists of variables and parameters. The method for solving MLE requires us to find the likelihood and the log likelihood. Say we've got parameter theta that we want to find. And theta can take all the values from here all the way up to here. Okay? And this, say, the likelihood looks like this. Maximum likelihood says we have to find the likelihood function that maximizes this likelihood function. So in this case, our solution would be about here, because at this point, this function is maximized. How do you find that point? Okay, from high school maths, we know that all we have to do here is find the stationary or turning point. So find the derivative of likelihood with respect to the parameter, set to 0 and solve, and that gives us the point right here. Okay, so that works like majority of the cases, especially for an undergrad, but if you're unlucky enough to be in a course that gives you something like this, then you can't do that. So say that, here's a second example. Say this time my likelihood looks something like this. And I try to use the method of differentiating. Then I'm going to find this as a solution. I'm also going to pick up this turning point as well. But the thing is that that is not the solution. That does not maximize the likelihood, because the solution in this case will be right here. It is what we call a boundary solution. Okay, something that would have helped is if I told you that for any model, if there is a restriction on the values that our parameter can take, for example here our values can take here to here, this range interval of values is called the parameter space. The parameter space here would be all the way up to here. So you can see that for the first case where we use the derivative method, that works because our solution is not on the boundary. It's not here, it's not here. It's what we call an interior solution. It's inside the parameter space. Whereas this case here, our solution lies on the boundary. Okay, so obviously you're not going to be able to find it using the method of derivatives. So now you know what the problem is. Let me give you an example. We have a random sample and it follows this. This is the marginal density. There's a one parameter here being theta. And the random variable, the x's, they can take values from theta and they're finite. The parameter is finite and positive. We're asked to find MLE of theta. Okay, the usual way that we solve this then, step 1, write down the likelihood function. L, capital L for likelihood, and then theta the parameter. Recall that this is equal to the product of the marginals. Okay, random sample here, it means the x's are independent. Okay, so then this is equal to, and then we just do it. Substitute this into here. Right, I just want to pause here. What you do when you see this is you write this guy here and you do a subscript on the I. Subscript on x, so you stick an I there. Alright. When you get a question like this means just for a given x, so they don't, instead of writing like I here and I up here and saying for every I. It's just usual, it's more common and less clumsy to just omit that I, because you're just supposed to know that's for any of I, okay? From I1 to N, for all observations. Okay, and just to say that, I'm just saying this because I've seen a student this week who completely didn't get it. This xi from I1 to N, x1 is a number, it's a label. x2 is a number all the way to xn, okay? It's not true to say that x1 is equal to 1, x2 is equal to 2, all the way to xn is equal to n. That's not the data. They're just the x1, x2, xn, they are just labels for the data, okay, which could change from sample to sample. Okay, so then this is equal to e, and in the exponent we have minus sum of xi plus n theta. If that was a bit fast for you, just look back at my previous video where I do it slower for some other examples. Then what you would do is we take the log of this likelihood function denoted by little l. You can see that it's equal to this. Okay, that's step 1. Step 2 says that we find the derivative of this guy with respect to the parameter being theta, not x. Okay, so let's use this notation to say derivative with respect to theta. Well, the first term is 0 with respect to theta, and the second term it comes to n. Now, a usual way of solving this thing then is to set this guy to 0 and solve it for theta, alright? But can you see that I've got a problem here, because this expression does not involve theta, so you're stuck, aren't you? What do you do? Okay, well, let's just kind of think back to high school maths. If this is equal to n, n is a sample size, it is a positive number, so the main thing it's positive, it tells us that the slope of our likelihood function is positive everywhere for all values of theta. If we look at this likelihood function and sketch it now, theta, can you see that this is the formula of a straight line? Theta is like in your formula of straight line, y equals mx plus c, that is my y, x is my theta, n is my slope, and that's my intercept, which is a minus number, so it could look something like this. Alright, so the intercept right here is minus sum of xi, the slope is of gradient n, it's positive. Okay, so it doesn't look like right at the start of the video where I said, oh, it looks like this, you can find the turning point and solve. It doesn't look like that at all. So this is, the thing is right on, the solution is right on the parameter space, on the boundary of the parameter space. You can see from here, this picture, that the solution is right here on the maximum value that theta can take. Alright, we're told that theta is finite and positive, so it can't be negative values, so it starts from 0 and all the way up to whatever this value is, and that will be my solution for theta. So let's finish this question off, and then I will tell you how. Then I'll just talk about it generally again. So the solution is to get the maximum, to get the maximum of the log likelihood, we need the maximum, we need theta to be as large as possible, yeah, large as possible. But it's also got to be, we can see from question here that the theta has got to be less than or equal to x. So it's got to be as large as possible, and at the same time, so this is the restriction, that theta has to be less than or equal to all my x's. And x's I've got in my sample, I've got n of them. Okay, so we want to choose the biggest theta that we can get, but at the same time that theta that we choose must be less than all these x's. Therefore, using logic, it means that my solution, so theta hat, must be is the minimum value of these x's. It's the minimum value of the x's over all these x's in the sample. And that's the answer. So the largest theta, the MLE is the largest theta, which also satisfies this constraint that it's less than not just one of the x's, but all the x's. And the only theta that can do that is the one is if we choose it to be the minimum of the x. So we've seen here a problem where the usual method doesn't work. We can see it doesn't work when we try a usual method of derivatives and we come out with an answer that does not depend on our parameter. And in then that case, for simple problems where we have one parameter, we can try sketching the function of the likelihood, log likelihood, and that we should be able to see then that it's on a boundary, and then we make the argument, and that's it. Let's do another example. This is taken from a first year undergrad past paper. Let these x's be a random variable from a uniform distribution on the interval minus theta to 0, where theta is positive and we assume finite, and it's an unknown parameter. We're doing part 2. Find the MLE for theta for 5 marks. So here I've drawn the density for x. X comes from a uniform distribution between 0 and minus theta. That means if I pluck out values of x from here, they're going to be between 0 and minus theta, and these x's are going to be negative, aren't they? They're going to be negative values. Xi's are negative values between 0 and minus infinity, minus theta. Okay, we'll recall that the density for a uniform marginal distribution, fx is equal to 1 over b minus a, well that's the upper limit and that's the lower limit. So here our a value is over here, our b is here. So what we have here is that is going to be equal to 1 over theta. And we want to say what values of theta that we can have. Well, you can see the question told us that the theta has to be less than or equal to minus theta, so be less than or equal to the x's. Alright, I'm just thinking whether you can see that. Because it's a uniform distribution between 0 and minus theta, that's the lower limit. It must mean that all my x's, I told you, they're negative values between 0 and theta. So I could have an x here, x here, x here, pluck out all these x's. They can't drop below minus theta, so that's why minus theta less than or equal to these guys. We're going to need that, because remember when you do a likelihood you always need the marginal, so that. Oh, also to stick with consistency I should put comma and my parameter theta. Okay. Right, well if it's 1 over theta, that means that this height here is 1 over theta, just to get a bit more of an idea of this, get a feel of what we're doing here. Let's try to solve this in the usual way, a likelihood function. We're also going to assume that, yeah, these things are random, okay, independent. So therefore likelihood is the product of the marginals. Product of the marginals, you can see you could do that in your head, that's even 1 over theta to the n. Let's just write that theta minus n to help us do a derivative. And in this case, there's no point taking a log of the likelihood because that's not going to help. That doesn't make life simple at all. This is easy already as it is to differentiate and solve if possible. So therefore, the derivative of this guy, capital L theta, is take that n minus n down, theta minus n minus 1. Now this guy does involve theta, it does involve the parameter. The usual way then is to set this to 0 and solve. But if you do that, then my value of theta is it says that it's a very, very big number, and in the limit the answer is infinity. Okay, so infinity is not an answer, so let us, well, it's not an estimator, so let's get rid of that and rethink about it. This guy here, theta, is positive. We're told it's theta in the question. Theta is positive. N is positive. You've got a negative here, that means this is negative, okay? So it's telling us that the slope of the likelihood function is down. Okay. Also, if you try sketching the likelihood, before in the previous question we sketched the derivative of likelihood, but this time let's sketch the likelihood. Depending on the question, you sketch one or the other just to help you see where the boundary solution is. So theta, and I'm drawing it from 0 because theta, you told the question, is non-negative. This guy here, power function is like this, isn't it? Okay, 1 to the theta over n. And so for a value here, because we've got to say what the parameter space is, it doesn't join up to 0. At some point here it just goes bump down here and line down here, so there's nothing. It jumps up here and goes up here. Clearly from the picture you can see there is a solution. The solution is right here. This is the value, whatever this value is, that maximizes the likelihood function. Okay, so now we've got to put this in words. So we want the solution, theta hat, is going to be the smallest theta we can get away with, such that we know that this minus theta has to be less than all these x's, such that minus theta has to be less than all the x's. Okay, well, we don't like this negative because we want that answer in terms of just theta. We want to say minus theta is something, okay? So let's multiply both sides of this inequality by a positive, negative 1. So that's such that this, and multiplying it by minus 1, is the same as saying positive theta is bigger than or equal to minus each of these guys. Now if we think about it, this is a positive number. Before, I've told you before that the x's are negative, so if we do minus a minus, that's plus. So all these minus x's, they are positive. And I just want to kind of make up some data as well. Let's pretend we've got three points. So since I'm doing this off the cuff without I'm just doing this on the first take. Okay, so minus theta I think it'll be instructional if I just give you an example. Minus theta is less than x1, x2, x3 all the way to xn. Okay, and we just said that is the same as saying that theta is bigger than or equal to x1 all the way to xn. And if we just think about some data, pretend we've got the numbers in our sample 531, minus 531, because the x is a minus figures. So then over here, our numbers that will become 531. Okay, so what is the smallest theta that we can get away with, such that that theta has to be bigger than all these x's? It must be that the solution is the maximum of this. Must be the biggest value of these I've got my minus of these minus of the minus x, over all the i's. Just better slow down, and you might have to just stop the video and think at this stage. From the likelihood function, this picture, we can see that the solution, the MLE, is the smallest theta. But the theta is constrained because minus theta has to be less than this. It's the minus here that kind of makes this question harder than it is. So minus theta less than this is the same as this. To say that we want the smallest theta such that all our theta must be bigger than each of these values, must be that it must be the maximum. Okay? It can't be the minimum, because if it was the minimum, that means there are some x's which are bigger than it, and then this is not satisfied. What would the solution be right here then? The solution would be 5. Okay, that's the maximum here. If I pick the smallest, 1, then theta is not bigger than 3 and 5. If I picked 3, then 3 is not bigger than 5. So that's the answer. Writing this is equivalent to writing minus the minimum of xi. Okay. So if we looked at our xi's in our example, minus 5, minus 3, minus 1, the minimum there is minus 5. If we take minus 5, that's plus 5. So that's the same as the answer I got right here. But just say that's the MLE. Okay. And also just to note, this is to help you if you're really thinking about this through. This following, this would be like a true or false question in one of my classes, but let's see if you can get minimum of xi. Is that equal to the minimum of minus xi? The answer, well, let's look at it. Minimum of minus xi in this here is minus 5. Minimum of xi here is 1. You take the minus of that, that's minus 1. Minus 1 clearly is not equal to, let's see, where is it? Minus xi. Minus xi. Oops. Just to rewind there. I tell you, this is tricky, this one. Minimum of xi, I'm looking over here. Minimum value of xi here is minus 5. Minus that, I get the answer 5 on the left hand side. Minimum value of minus xi, right, I'm looking along here. So in my example, the smallest value is plus 1. Alright, so clearly they're not the same. So this is not equal. Okay, so just to round up, if you have the misfortune of having one of these questions in an exam, you try the usual method. If you get a derivative that doesn't make any sense, you can't find a finite solution, or it doesn't depend on the parameter, try sketching the likelihood over the parameter space, or sketching the slope as we did in the first example against parameter space, and just see from that where on the boundary the solution lies. So sketch the likelihood or log likelihood. Okay, I think I was saying sketch a slope, but I'm obviously falling asleep. Sketch the likelihood or log likelihood against the parameter space and see at which end of the which end of the boundary you are looking for, where the solution lies. Okay, so before I actually nod off, I wish you good luck, and that's it.